Hello and welcome to Preprints in Motion. Join us as we sit down with early career researchers and discuss their latest preprint and find out about their journey through the muddy marshes of academia. But we don't stop there. Every month we'll be bringing you special episodes with open science leaders where we discuss how to fix academia. Easy, right? So hit that subscribe button, leave a rating, or find us on Twitter at MotionPod. But for now, let's get into the show. This week, we dive deep into DNA recorders, and no, that is not a musical instrument, with very soon to be shiny new PI, Teresa Lovelace. This is really great because I knew nothing about sort of DNA recorders before reading your preprint. I knew they existed, and that was about it. So this is going to be a lot. I'm going to learn loads. It's going to be great. So thank you so much for joining us and giving us your time, especially in between applying for jobs. I can only imagine how stressful that currently is.
It's also fun. So
hopefully your interview the other day went well.
I think so. We'll see. It was one of those. So nowadays they do Zoom screening interviews in general where you talk for 20 to 30 minutes with the search committee. So it was just one of those. But yeah, we'll see.
Fingers crossed.
Thank you.
But we'll start with the fun fact you supplied because it's amazing. You have 39 first cousins. That really is a big family. I counted mine just before you came in, and I have 11, and I thought that was a big family.
I mean, it is. Yeah, my mom has 8 sisters.
Wow.
And my dad also has 3 siblings. So yeah, no, it's great because it means, at least in the US, and actually now to some extent in Europe, I have a cousin everywhere. So when I moved to Orange County for my postdoc, I'm from Phoenix, Arizona. So we're about a 6-hour drive from there where we live for my postdoc. But I have a whole family of cousins here. And, COVID has made meeting up more difficult, but we still get to see, my kids and their second cousin get to hang out sometimes. And yeah, no, it's great. And then in grad school in San Francisco, I happened to move onto the same street as my aunt. And so we would meet up with multiple cousins there. Like, it was great. Yeah.
Big benefit, especially in science, where can be quite lonely. So having cousins everywhere is great.
Yeah, exactly. No, you get moved to whatever city and actually, yeah, even so I have one job offer and so far, and in the city where that is, my husband has a first cousin who also is about to have a baby. So yeah, they're everywhere.
There you go. So we're talking about your recent preprint where you looked at DNA record. Well, you created a DNA recorder, but I think it would be sensible for mainly my benefit, but also maybe people listening, if you could explain what a DNA recorder is and does.
Absolutely. Okay, so in a broad way of thinking about it, this is a reasonably old field, but it's had a huge flowering in the past few years as a result of CRISPR-Cas9 and the general excitement around that new technology. So basically, a DNA recorder is just any technology that you put in a cell that takes a transient event in the life of the cell and turns it into a permanent mutation in that cell's genome. So the simplest way to think about that is something like if you express a specific transcription factor, it's going to be hooked up to some kind of reporter that, for example, will lead to the expression of CRE that then is going to do some recombination in that cell's genome and lead to a permanent mark. So this is why I say, to some extent, this is an old technology, because for a long time, people have been using mouse lines, for example, that mark specific lineages by having an inducible CRE that then will change something like a lock-stop-locks cassette to lead to permanent expression of GFP. So starting in 2016, people have started using CRISPR-Cas9 to lead to sort of a much more diverse set of potential permanent mutations as a result of transient events. So there was a really key paper that was joint between Jay Shanduri's lab up at UW and Alex Shear's lab, which I think at the time was at Harvard, and they've now moved to Switzerland. But basically, they took zebrafish and put into their genome a cassette of many Cas9 target sites, and just very early in the zebrafish's life, they injected Cas9 with a guide RNA to allow sort of random editing in each cell, leading to sort of a different barcode in each cell where this editing occurred. So essentially, there's two ways it can be random, right? So there's multiple target sites. So which target site gets edited is going to be different between cells. And also, once you get a Cas9 cut, then the host DNA repairer comes and repairs it, and then you can get different potential editing outcomes. So the actual mutation made is going to be variable. So essentially what they did is very early in the life of the zebrafish, they basically tagged different cells with a different barcode. And there were actually several versions of this that came out as preprints at the same time, as I'm sure multiple people were working on this in parallel. And there's sort of slightly different ways to do it. Something that I think represents a totally different approach, or a sort of different family of approaches, is one in which a couple groups, so from Tim Liu's group, MIT, and then Reza Kalher led it in George Church's group, they made a Cas9 guide RNA that was self-targeting. So essentially, the DNA that encoded the guide RNA actually is also the target for the Cas9 guide complex. And so that allows you to get multiple rounds of targeting of the same site. So the idea is that you make the guide, it directs Cas9 actually to its own template. And then when any mutation is made, it can then transcribe a new guide that still exactly matches the target site. So you can come around and get another round of editing. And that leads to more potential editing outcomes. And therefore, if you think about starting with one cell that has this synthetic self-targeting guide RNA, at any point when you express Cas9, as that cell is dividing, you can progressively accumulate further diversification of that locus so that you can get many potential editing outcomes and sort of tag different cell lineages and distinguish them from each other. And so basically, I can keep going at how this ends up leading to now our approaches in sort of sequential editing where you can keep track of the sequential edits. But yeah, there's been a lot of work in the last few years.
We're going to get to that bit.
Okay.
Jay's lab seems to be everywhere.
Yeah.
During my first postdoc, I started to get into chromatin remodeling, things like that, and it was just everywhere. Like every other paper was Jay's lab. It was insane.
Yeah, no, they've been really at the forefront of like several different ways in which both genome editing and CRISPR screens, and also sort of enabling single cell analysis and interpretation.
So have you got a nice concrete example of what you would use a DNA recorder for? I mean, you've kind of touched upon it anyway in that first answer.
Right. So some really, really good examples that I think, especially right now, Jonathan Weissman's lab has been using them for, is any situation where you have a big population of cells, and you know that a small fraction of them are going to go on and take on a new cell fate of some kind. And you don't know which cells are the ones that are going to seed the new cell fate. So a great example of this that there's been, I don't know if the second paper is out yet, but one paper and one recent preprint from Jonathan Weissman's lab where they took cells in a primary tumor and then tracked what they were doing as they became metastatic. So at this point, they're mostly using the DNA recorder to keep track of cell lineage. So it's essentially making random edits that will allow you to see the relationships between the cells, which tells you basically, if you're looking at metastatic cells, it will tell you how metastatic they are, because you can say like, how many places in the mouse's body do you find all of these closely related cells? And they also tell you, you can find sort of the really informative cells, which are clones where one closely related cell became highly metastatic and one did not.
Yeah.
And then you can use single cell RNA sequencing to look at the real key differences between those cells. So hopefully in the future, what we can also do is say, okay, we have some hypotheses about the transcriptional programs that are really essential for driving these fate changes, and we can actually record those as well. But basically, any situation where you need the cells themselves to tell you which ones are going to acquire the new phenotype. So you can't just like take time points because you don't know which cell in each group is going to be the important ones, but you also want to know what they were doing in the past that made them do that, is sort of the paradigmatic example.
I was going to say, can this be used with I do a lot of differentiations. So I guess that could be a nice way, because we do a lot of single cell with different cells and we see at certain time points, like what is expressing what, but this could actually link it back to an earlier group, I guess.
Absolutely.
Follow it all the way through. It'd be really, really handy.
No, exactly. Like any situation where some of the cells, but not all of them, will undergo the fate switch. And especially where you can't take time points because, for example, the process isn't synchronous, or it's happening in an inaccessible location, like inside an organism.
Or 3 a.m. in the morning. I've done a lot of that.
It would be even better. Yeah, exactly. It's like, is it accessible to me because I'm asleep in my bed?
We need to start getting people on who do like microscopy techniques, because every time we have somebody on, Emma seems to pick up a cool new technique she wants to use.
Yeah, totally. And also in terms of like, from my perspective, I'm always trying to find applications where we can get stuff like get a new technology quickly into a biological question. So anything that's ex vivo is like awesome. Although I think we're using tumor xenografts is also something where you can pretty quickly like put the new technology in the cell and then put the cell in the animal in this case.
Yeah. So in your preprint, you've got a list in the introduction about all the things that a good DNA recorder should be. And then you want to state that the existing recorders can't do them all. What was the limitation that meant they couldn't do them all?
Yes. So basically, the idea of continuous operation and being able to record events in order were challenging because previous recorders either can only do at each location or each target site can only do a single operation, right? So in the sort of traditional, as of 2016 DNA recorder where you have a single or a series of DNA target sites that Cas9 can target, essentially once it makes an edit, then that site now cannot be changed in the future because the guide RNA doesn't match anymore. So that's one way it can be limited. Conversely, we had these self-targeting guide RNAs that can come around and do multiple rounds of Cas9 editing. But because in general, Cas9 makes deletion mutations, if you do one edit, and then the boundaries of that deletion mutation are sort of the new information or sort of mark that edit. If you come around to do another one, those previous boundaries will get deleted. And now you'll have a new edit. Yeah. And so essentially like you can't accumulate information at one site, which was the real limitation. And so we'd previously published, we pre-printed it in 2019 and it was published in 2021, in part because we got our reviews back like March 10th, 2020. So we couldn't do the experiments to respond to them as quickly as we would have liked. But so basically, like we'd modified self-targeting guide RNAs to make insertion mutations, which then does allow you to accumulate edits at the same site. But just due to how guide RNAs are, what happens is you can do a few rounds of editing, accumulate mutations in a few rounds, but eventually you get a long guide RNA, which like drastically reduces its efficiency because Cas9 doesn't like long guides. And we still had the same problem where you have a lower chance, but still a chance in each round that you'll get a deletion mutation. And because that's sort of a terminal state, eventually everything falls into the well of deletions. And after a few rounds, you have no loci left. Yeah. So basically what we needed was a way to edit a single site so that you can get ordered accumulation of edits, but not delete the previous information. And also don't reduce the efficiency in each round.
And before you answer the next question, which I think you might be about to do, how did you do that?
So essentially what we needed, and I should say now, which I'm sure this will come up, but like Jay Shanduri's lab also had the same realization that we did at the exact same time, which is that we needed a way to make a wide variety of edits that could be made into a continuously editing system that didn't make double strand breaks, because that was sort of the dichotomy in the past, where essentially you can make an edit that has many possible resolutions, right? But what you're doing is making a double strand break. And that always leads to the possibility that you'll get a deletion mutation that destroys your continuous editing. Yeah. Conversely, there were ways to make edits without double strand breaks, like with a base editor, but those had a smaller number of potential outcomes, and therefore it was harder to make them sort of accumulate extremely varied information in a progressive way. So when Prime Editor was introduced by David Liu's lab in the end of 2019, it was clear to us that this was an opportunity to kind of abolish this trade-off. So essentially, most of the original Prime Editor paper, they actually did use nicks on both strands that lead to a rate of deletion mutations that did not prevent them from doing extremely great editing, but was too high for doing many, many, many rounds like we wanted to. But even if you just don't make the second nick, so essentially just make a single nick, no double strand breaks, no any breaks on the other strand, you can get many, many, many different editing outcomes at an acceptably high efficiency. So yeah, basically I had heard a rumor that David Liu's lab had like something cool, but like no other information other than that, which I guess is like always the case. But
Yeah.
but basically so we'd been trying to figure out a way to sort of combine base editing and Cas9 cutting with TDT to try to like construct some kind of system that could have these properties. But when Prime Editor came out, it was like, oh yeah, that's the way to do it. It was very clear. So yeah, basically that's the enabling technology. And then we played around with several different architectures to find one that allows you to do, progressive rounds of editing without making double strand breaks.
So you mentioned double strand breaks are one of the ways that this can kind of cause a termination. How do you naturally stop this? Is it just when you take the cells to then use them for whatever you're going to do downstream, or can you encode a stop at a certain time point, for example?
Oh, you mean how do you stop editing?
Yeah, stop the recording aspect.
Yeah. So currently we haven't implemented any way of stopping, but there are ways that you could do it. So for example, if you wanted to stop editing, I think the way that I would do it is to just get rid of Cas9. So essentially you're expressing, in our case, Prime Editor, which is a Cas9 fusion protein. And if I wanted to say at time X, stop editing, but don't kill the cells, I think what I would do is just encode Cas9 in a way that could be excised by Cree and just get rid of it. Because essentially when you express Cas9 in a cell, it's going around and finding every single PAM, which, in the case of what we're using, Streptococcus pyogenes Cas9, the kind of standard one is NGG, right? So very frequently in the genome, and kind of starting to unwind it and checking if it matches the guide RNA. So I wouldn't want that in my cells if I didn't need it to be there.
Yeah.
You could do an inducible system, I guess, as well.
Yeah, exactly. And then turn it off.
Then just stop adding docs or whatever system you're using.
Yeah, absolutely. So we have made a version of our earlier system that has a similar setup where you just have to add this chemical that activates the hypoxia response pathway, and has the same result where you can like pretty firmly turn it off.
Yeah, that's really cool. I may have missed this, but so it's in a specific site that I'm guessing is like a safe harbor somewhere in the genome, so that it's not causing just kind of random mutations all over that may be affecting the cell.
Yes. So basically we target editing to a single site in the genome.
Yeah.
And the way that our system works, we actually can edit, in theory, any genomic site. We don't actually need a synthetic locus of any kind. So the idea is to target it to somewhere that is accessible to Cas9. So some regions that are like heavily heterochromatinized, for example, are less accessible. And so that would presumably reduce your efficiency. And then of course, yeah, absolutely, you need to find a place that's not going to harm the cell. And what we've done so far is just there's a site that we know is very accessible to editing and doesn't seem to have any phenotypic consequences. So we've just been using that, also because we already had primers that worked well, there's historical reasons. But I think in the future, I want to take advantage of the way in which our system can be used at any endogenous locus and try to take advantage of the highly repetitive nature of mammalian genomes to have, more than one recording site in each cell that can be targeted by the same recording machinery.
So is there a resolution limit to what you can record? So, do the events that you're recording have to be a certain time apart? I mean, obviously, I would suggest they can't be maybe at the same time, is my takeaway.
Yes. So basically, if we're just thinking about a single recording site in each cell, there are several limits to your resolution. So I should say, first of all, we have not yet actually recorded events per se in order. We've recorded different PEG RNAs, which are just Prime Editor guide RNAs. We've encoded like different transfection orders that we've done sort of as an artificial proof of concept. We actually I'm doing the transfection on Friday to put in, different inducible PEG RNAs so we can record actual events. And the limitations on resolution are several. So the first is sort of the baseline efficiency of Prime Editor with these particular sequences. So I say we're only getting about an average of 7-ish% of our loci to make an edit each day. So essentially, on average, each edit takes more than a week, like more like 2 weeks. And so in that particular cell, that's a real limit on your resolution. Although, in some proportion of cells, you'll have more efficiency and therefore, you can record more fine-grained events. However, that's something that can be improved. We've only begun to really optimize that. But there's also an intrinsic limitation to the temporal resolution, which is that it seems to be the case that after Cas9 is recruited to a target site, its half-life on the DNA is pretty long. So presumably you can't get another edit any faster than the time it takes for Cas9 to go there, sit there, and then the reverse transcriptase component of prime editor needs to make the new template, and then there's some kind of flap resolution, where the edited template competes with the original DNA to eventually incorporate the mutation, and then there's presumably some processing that needs to be done by the host repair machinery. And then I think another kind of intrinsic limit to temporal resolution is that very likely, so cells are evolved to not make changes to their DNA and to resolve DNA damage, essentially to limit mutations. So it's quite likely that prime editor and Cas9, any kind of editing goes there, and the majority of the time it's prepared without mutation, and so then it has to come back and try again. So I think that's really the intrinsic limitation, and the way that we want to get around that in the long run is to have multiple recording sites so that even if a particular recording site doesn't pick up on an event that's only several hours long, for example, one of them will, and you can get more of the picture by kind of averaging those sites. However, obviously you can only have ordered recording if you have for events that are at a single site, and so that's a trade-off that you need to optimize. But the good thing is probably even if you have multiple sites in the same cell, it's likely that the expression of Cas9 is such and the rate limiting steps of Cas9 editing are such that they're not going to compete with each other. So yeah, actually we're in the process of testing that directly now, just because I feel like it's something we should establish sooner rather than later. And actually an undergrad in the lab is that's her project, so it's fun.
So do you find any off-target effect with this? Are you getting anything that is perhaps being recorded that shouldn't be?
Yes. So that's another I think real advantage of having prime editor that only is making a nick instead of a double strand break. So what we did is this is figure 3C of our preprint. So what we did is we took every single sequencing read of our recording locus and then binned it into the closest number of rounds of editing, right? So anything that was a deletion, each edit makes a 20 nucleotide insertion. So anything that was a deletion or up to 9 nucleotides got binned into 0 rounds. Anything that was between a 10 nucleotide insertion and a 29 nucleotide insertion got binned into 1 round, et cetera, et cetera. And then we just said, is it the exact number of nucleotides that we expect, suggesting that it is the intended edit, or is it a different number? And basically what we found is that at each size, 99% of the reads were the exact length that we expect, and 1% were something different. And so essentially the number of unintended edits seems to be quite low, although there's obviously another kind of off target that we need to assess, which is just elsewhere in the genome, are we getting random mutations? And actually something that came up because we pre-printed this is that we are probably, and this is something that I should have realized much earlier, but that now we know and we have a way to fix it. But essentially, we are getting off targets at the loci that encode our PEG RNAs, but they're not really off targets. They contain the exact sequence that we're targeting. So this is something that very few people realize. Essentially, someone who is a potential collaborator who knows a ton about prime editing very kindly pointed this out to me. And so essentially now we have a way to protect the PEG RNA loci by essentially making nicks on the same strand, which just kills prime editing. So we'll defeat that off target, although that's something that it's one of those things that you get stuck in a way of thinking about something, and so you don't see it. But basically one person saw it. So grateful that we put it out there, because without having something like putting the whole story out there, I don't think there was enough information for other people to notice. But so that's kind of solved. And in the long run, we'll just put introns in the PEG RNAs. But once I have a system that I want to make into a mouse, for example, I'll do all the well-established protocols to make sure that the particular sequences I choose aren't going off elsewhere in the genome and causing trouble.
Yeah, you've just segued brilliantly into the section about preprints there. You're making my job very easy today.
Okay, I hope I'm not.
I love that. I love that when that happens. Some people make it really difficult. So you've touched on the benefit of having other people being able to look at your work.
Yeah.
So have you had any other experiences with preprinting so far? Is this the first paper you've preprinted?
So it's not. And actually I had a great experience the last time too. I touched on it a little bit, but we made a previous editor that made ordered continuous insertion mutations, but other than that has basically nothing in common. It's a totally different architecture. And what we used previously used a self-targeting guide RNA, and then we expressed Cas9, as all self-targeting guides do, but then also TDT, which is a DNA polymerase that instead of using a template, just binds to double-strand break ends and adds random nucleotides. So the result of that was instead of getting rounds of deletion mutations, we got rounds of insertion mutations that actually do accumulate in order. So that basically, we got the key result in that work near the end of 2017, early 2018. And then, there's a lot of follow-up and demonstrations that we wanted to do. And essentially, we spent about a year really trying to figure out how to have large populations of cells and then split them in a known pattern and then try to reconstruct the pattern from sequencing the recording locus, which actually ends up being much more technically challenging than you would think. Because essentially you have, if you have two populations of cells that are related to each other, you have to capture a pretty large proportion of both populations in order to get the ones that are related to each other.
Yeah.
So that's technically actually difficult. And so we finally, I learned a lot about amplicon sequencing and so basically, we were ready to publish that. We were ready to have a reasonably final version of that in about April 2019. And I will say, my daughter was born in August of 2018. So that probably didn't, help my efficiency, but totally worth it.
It would be good. It's good you said that, because if you said it wasn't worth it, in about 18 years' time, you would have regretted that.
Oh yeah, no, she'll search, and no, I'm always expecting her to run in here, but I also have a 6-year-old son who I also is wonderful. Just for future reference. But so we were ready in May 2019. We got everything together and put it up. And then we had some things we wanted to kind of improve, but we really wanted it to be out there. I also made sure everything was available on Adgene at that time. And we actually had people requesting it right away because I'd been talking about it for a while. So I feel like, people who were interested kind of knew about it. And I just wanted everything to be available, right? You want people to be able to use your work. And
you were the cool rumor for a while.
Yeah, exactly. But you want to be a known thing, especially if you're not able to, if it doesn't immediately go into a journal. So essentially, we spent a really long time submitting it one place and then hearing back and et cetera. So yeah, it was great to have it pre-printed. And essentially by the time we got it at its perfect home, Nature Chem Bio, one of our reviews was even this has been on bioRxiv since May 2019 and people are using it and it's great, so yeah, it was perfect. And especially because of COVID, right? Because essentially we got reviews back in March of 2020, which under normal circumstances would only have taken a couple of months to respond to. But then between not being able to go into lab for several months and then all of these, we had shifts and we also, everyone obviously has experienced this. We also had supply chain issues where we couldn't get necessary components. We wanted to do a nucleofection and the shipping of the samples from Germany took, a month instead of a week, all this kind of. So it was really nice that it was out there and, people could use it or, look at it and come up with something of their own or whatever. And so when it finally came out in March of 2021, it was much improved by the review process. But, the essential thing had been out there if people really, were right in the field, they sort of knew about it already.
I think that's one of the biggest benefits of them is that you can, people can use it straight away, which is great.
Yeah. And in this case, pre-printing was, in the case of this paper, essentially Jay Shanduri's lab has 2 back-to-back papers that have, I think, fundamentally a different architecture. And I think we're going to end up being the right choice for different applications.
Yeah.
But it was very important that when they deposited their preprint, we could deposit it an hour after they did, or after theirs came out. And, kind of just, obviously we independently came up with this general approach, and it's nice that we're both out there. And also obviously for applying for jobs, it's been really nice to have a preprint that I can point to in both cases. And, although it wasn't actually out when I submitted most of my applications, now that it is out, I feel like when I go on interviews and stuff, people who are in the field have already looked at it, and it's really helpful to kind of get everything out there.
And you've done what to us feels like a long PhD, but it's just an American PhD.
It's a long American PhD too.
So that was 7 years?
So yes. So basically it was really 6.5. So I resubmitted my second paper. Okay, so first of all, so obviously, with American PhDs, you spend the first year rotating.
Yeah.
And then what I ended up doing was fairly early on, I had an interesting result. And I came up with a whole thesis proposal that involved saying, wow, we can get activation of the DNA replication checkpoint without either of the two known activators of the sensor kinase. And it was like, this is interesting. We're going to do a screen for the other activator. And then I think the real answer is that the other activator is just the replication fork. So essentially, there wasn't, we were potentially doing a screen that would have shown just that it's not necessary.
Yeah.
And there's more stuff to work out there that I think people have done subsequently, but it wasn't that wasn't the thing that we had the tools to find. So we published a paper just showing our results, but then I was kind of 3 years into a PhD and kind of either done or needed to start something totally different. So then I started a new thing, which was actually in human cells, which our lab had previously never worked with. So there was a lot of I need to figure out how to get a tissue culture hood and so there's a really kind person who was retiring who eventually let me sort of inherit his tissue culture space. But I finished that project and sort of resubmitted the paper and then had a baby 6 weeks later. So my son, totally worth it for
that's 2 PhDs and a baby. It's amazing.
No, well, I mean, they both really, I think they were both really important and learning different things from them. And then I came back to wrap some stuff up. I took a leave of absence for 5 months as a maternity leave. And then I came back to wrap some stuff up, but I was basically done after 6.5 years. But it was really nice to come back in a place where I knew things, where I could get used to being go to drop off at the daycare and juggle all this stuff and then also be applying for postdocs. And so then I've done a really long postdoc as well. But honestly, just this has been so good. I've learned so much at each step of my PhD and postdoc. And I just think it's a real barrier because frequently they're so poorly paid.
Yeah.
And I just I wish there was a way to kind of, in most fields, you don't become the head boss of everything as your second job, right? But you get paid, in a way that can allow you to pay off student loans if necessary, or have a family or whatever, support other people you care for. It just, I don't know.
There's a new postdoc started at work this week actually, and she's from America, and she was talking today about her student loans, and it was horrible. They're so big.
Yeah.
There's so much money that you have to pay back, and the whole system just seems terribly designed, especially if you go into science and don't earn enough to really pay it back.
Well, it's and I should say, I've been really fortunate to not need student loans, and it's just a total game changer, right? To allow me to do this really long postdoc. And it's just another way that you reinforce inequality based on, the income you had growing up. And it's just ridiculous. And I don't know. I'm curious about, I know in some countries in Europe, there's sort of professor positions that you're still sort of working with someone in a larger lab setup that seem potentially interesting.
So we've got some of the fellowships we can apply for. They're a bit like a semi-independent postdoc. So
okay.
It's your work. It's your project. You've got your own money, but you do it under the guidance of somebody who's more experienced. So it's a lab within a lab situation, really.
Right.
It depends where you do it. Some places will treat you like a postdoc. Some places will treat you more like a PI.
Right.
So sometimes you can get students, sometimes you can't. Very helpful. But yeah, we have those, which are, I think they're really good, but they're also, the main one in the UK, the funder changed how they're funding recently. And they shook it all up so that they've kind of gotten rid of that, and they've replaced it with one that now has you can only apply within 3 years post PhD, which is, it rules out so many people.
Right.
And then they're never going to fund me anyway because I keep complaining about them. So I can keep doing it.
I feel like that shouldn't be a factor, but yeah.
But yeah, so we've got them, but they're not. There's not many of them in the UK, which is a shame because I think they would be really good. But most of it is similar to everywhere else, where it's either you go lectureship route or the PI fellowship route.
Right.
Which are both pretty good in the UK, actually, if you can get them.
Yeah, no, I just feel like we're sort of, in the US at least, just the way that it's set up, it's almost requiring a sort of gentleman scientist like aspect where you're sort of like, I don't know. It just seems really unequal.
I think that's the case. I think just science is horribly unequal still, which is a huge shame. I mean, I think you're the first person we've had on since all this has come out on Twitter. But what do you think about the recent shift we've seen from a lot, certainly in the US, a lot of professors leaving their jobs to go and work at the new sort of startups that are just popped up
like
recently?
Altos and
yes. I mean, what are your thoughts on that?
I mean, I don't know enough. I think about what it's like to be a PI in the US. I think I'll find out soon. I have heard the quote that, like, you spend a year writing an NIH grant and probably resubmitting it and all this stuff, and they give you, $1.5 million.
Yep.
And you can spend like 15 minutes with a VC and they'll give you like $15 million. So I think there's probably, I don't know to what extent it's just that if you have plans that require a lot of money, there's not really a different way to do it than to tap into this private setup. Or if it's something sort of more pernicious where you feel like, I know there was a quote from Sime Chow, who's starting Arcadia, on Twitter, where she was saying during the pandemic, especially, she felt like she couldn't do right by her students and postdocs in academia the way that she could in private industry. And so that's something that seems like a deeper potential problem, where the sort of large bureaucracy of academia doesn't allow you to do things that are clearly right and required.
Yeah.
And that, I don't know to what extent that's general, and whether, that's sort of a necessarily better in industry all the way, but certainly something like pay disparities, right? Like seems, or the way in which having like a long, poorly paid trainee period
yes.
is intrinsically unequal is like something that can be fixed by having things be privately funded. And I don't know.
I think being a trainee when you're in your 30s and you're also considered a world expert is just insulting. It's one I hate it. It's such a backwards way of thinking.
Like, I never thought of myself as a trainee as a postdoc until kind of Johnny had kind of said, yeah, we're still training, because I guess we're kind of training towards a PI ship. But then I'm also not convinced that the way in which I like being at the bench, and like I'm not sure if being a PI is the next step for me. So like it's like it feels like it's kind of veering off a different path rather than I'm getting what I'm getting trained for if I'm a trainee, I guess.
And I still don't think we really get trained for that anyway.
No, I don't think we do.
Not
not
particularly well. Yeah, well, yeah. I mean, it's often it comes down to whether or not you're working with a PI who's nice enough to support you enough to do it. And not everyone is lucky enough to do that, unfortunately.
Which seems like another aspect of academia that's potentially really flawed, where like there's this, there's a lot of variation in your experience based on who you end up working for, but also they have so much power over you.
Yeah.
And, I mean, this is why I think I've had such a good experience in my postdoc, is that I really I got extremely lucky to work with someone who's like very, very serious about making sure that you get exactly the training you need to achieve your goals. And that was a lot of luck. And also that I really prioritized searching for that as when I was looking for a postdoc. But so frequently that isn't what you're getting trained for, right? You're getting trained to like be really productive at the bench, which is awesome. But also then it's confusing why you're not just a person working at the thing that you're an expert at rather than
getting paid more to do it, like in industry.
Yeah, exactly.
Yeah, we because there's some strike action going on in the UK soon.
Yeah, here too. Yeah, I don't know. Like the University of California students just like successfully unionized.
Yes.
I became disabled from essentially like I messed up my hands by doing too much pipetting as a grad student, which, like that's a thing that happens. That's totally fine. The issue was because I wasn't an employee, no one knew what to do with me in terms of just getting basic accommodations so I could keep working. And having like a place who could advocate for you is why we need a union.
Yeah.
Also, there's things within the UC that they know about, but that they need to really fix. Like their, I don't know if this ever happens in the UK, but their payroll software frequently just doesn't pay students for months.
We sometimes have issues with PhD students getting paid on time.
Yeah.
I've seen that come up a few times.
And it's like, people need to pay the rent. This is not... So having someone to, you need someone to advocate for you if you can't trust your institution to necessarily, pay you, for example. And frequently, I mean, that's another example of where you just need a good PI, because frequently the way that the only way that can work, right, is your PI will literally pay your rent for you.
Yeah.
Which, like, what?
We so there's a PI at Sheffield who he would occasionally have students stay, like PhD students who are at the end of their time, stay with him because obviously they'd run out of money.
Oh my gosh!
And it's particularly students who are foreign, for example, and maybe they don't have any family in the country.
Yeah.
So they would have to stay with him just to get through to the end because they'd run out of money, and it was a ridiculous way of doing things. Very nice that he would do that, but ridiculous way of doing it.
It's just you shouldn't be required to think about these things, right? I
No.
mean, it's your responsibility, I think, as a PI, but also we should just have a system that pays people's salaries and make sure they're, in the US, obviously, health insurance and continuity of health insurance is a huge deal that is often also messed up, either by the sort of intrinsic, like, shifting nature of trainee contracts or by, just badly working software in the case of UC. But, I spent so many hours on the phone with various people because I changed titles and therefore didn't have health insurance on paper for like a month and a half. And it was just like, what is this?
Yeah.
I mean, that's just like a very US story, but
it's all right. It makes us feel slightly better about ourselves for a bit.
Yeah.
It's desperately needed in this country at the moment. We'll take anything we can get.
Well, if it helps at all, I have needed a migraine medication for 4 months, and it's coming today, I think. But the company whose job is to keep costs down and therefore has been like negotiating with me about whether I can have this medication, and is also the company that is the pharmacy that supplies it. So imagine you had a company and you got paid for not doing your job.
Yeah.
It has been fun.
Yeah, the whole US system is just crazy.
Yeah, as Brits, we look over at the US healthcare and we're just like, oh my God. Like, oh my God.
I don't know, if I ever have any spare time, I want to just be like a volunteer, like, fighter with insurance companies for people. Cause like, I don't know, I just feel like I have all this like very pointless expertise. And it's like, I don't even know how you do it. I mean, I don't know. I mean, like, I've been fortunate to have like a little bit of spare time and like some familiarity with these like ridiculous contracts and stuff, where you have to call them up and be like, excuse me, can you tell me in the plan documents where it says that I owe this fee? Because it clearly says that I don't. But like, I don't know. I feel like a lot of people don't have time to do that. Or like, I don't know. Anyway, so I don't know if you have other questions. I feel like
we've kind of veered off, haven't we?
We've totally veered off. That was all my questions anyway.
Okay, cool.
I enjoyed our discussion. It was very...
Who doesn't like talking about the ridiculous's of the American healthcare system?
Yeah, no, it's
mind-boggling.
No, but oh my God, I'm so happy. I really hope my medicine shows up because I've had a migraine more days than not for like 3 months.
Oh God.
It's okay. It's like I can usually work through them, but it's just the stress. It's totally just the stress of like being on the job market and then having to like write this paper and get it out because we had this competition and like all this stuff. But oh my gosh, I'm so happy. I hope it works. But yeah, I mean, I don't know. I mean, I think to some extent the fact that stuff is so expensive here does to some extent subsidize the R&D, but then it's just a question of like, yeah, like, is it really? I don't know. Like, it's also
like, we hope maybe that's what's happening, but we don't know for sure.
Yeah.
Right. It's like, I'll be much happier about it if that's the case. But...
Yeah. With your interview, I hope it went well. It went well, and I hope it's positive and fingers crossed for you and everything.
Yeah, thank you. So I already have one offer. So I'm going to be a PI.
Yay!
For sure. But the question is just like, where and all this stuff.
Where's the favorite cousin living? That's the question.
That's the question. Right? I don't even, I mean, I can't say who my favorite cousin is but here is a really good place for cousins.
If they all listen on the same day, we might just break the top 20 in the US. So that'd be great help.
I should really get them on that.
Well, thank you so much for your time. I've enjoyed this chat.
Yes, thank you so much. But yeah, and good luck with your postdocs, and obviously you're doing a lot more outreach than I am, but
we try. Maybe it digs into my lab time a little bit sometimes, but it's worth it, I think.
It's part of the job, right, of science broadly.
Yeah.
And I hope I didn't say anything that wasn't true, but I don't think I did.
So I've definitely done that before, so it's fine.
Cool. I always just worry that I will like miss someone else's contributions and like not properly credit them.
Oh, it's okay. Oh, when I got it wrong, it was my own work. It's fine. It was on the radio. It was on the radio. I got completely the wrong number, and I had to tweet at them afterwards to say, "I'm really sorry, I was wrong." Highly embarrassing.
Well, I mean, that's the right way to do it, though. Like, they're wrong so much. Yeah, no, that's totally awesome. Thank you so much.
Right, thank you so much. Okay, and that is the show. If you enjoyed listening, then hit that subscribe button for more and leave us a review on whatever platform it is you're listening on. You can reach out to us on Twitter at MotionPod or online at preprintsinmotion.com. Didn't enjoy that? Well, we're all scientists here, so send us your review and let us know what works or what you'd like to hear more of, or less of. But until next time, have a good week.
Where do I find out about the different bioarchive licenses? This CC, BY, CDXY nonsense is driving me nuts.
ASAP Bio have a resource for that.
Ugh, that's your answer for everything.
That's because they have everything you need to know about preprints.
Sure, they probably have the basics, like info on the preprint servers, but what else is there?
There's so much more. Looking to post a preprint but not sure what different journal policies are? They have a collection to help you out with that. There are meetings around preprints and associated services. If you want to know how preprint adoption has changed over time, there's even a page on that.
And COVID?
They have a big section on preprints and the pandemic, plus some really cool infographics for communicating preprints.
And university policies? Surely they don't have that.
They collect uni policies where possible.
Okay, they do sound pretty impressive, but is it not a bit of an echo chamber?
It can be, but ASAP Bio also engage with people who don't love preprints and have concerns. So we had an excellent discussion on this very topic a couple of months ago.
Oh, is there anything ASAP Bio don't do?
Honestly, no, they're so nice over there. They were so quick to jump in and support this show. It's your one-stop shop for info on preprints and open science initiatives, so head over to asapbio.org to learn more and subscribe to their newsletter for the latest in preprint news. If you want a deeper dive into the world of preprints, then look out for the next recruitment of ASAP Bio Fellows.